500 million years ago, the oceans were ruled by animals unlike anything alive today. They had bodies armored in interlocking plates. They spread across nearly every ocean on Earth, and some of them carried eyes made from crystal, not crystal like, actual mineral lenses. Those eyes can still be studied today in fossils hundreds of millions of years old, preserving optical designs that scientists would not fully understand until long after trilobites were gone. And for a very long time, it seemed as though they would never be gone. Trilobites survived four mass extinction events. They endured environmental catastrophes that erased countless other forms of life. For more than 270 million years, they remained one of the most successful groups of animals the planet had ever produced. Then the fifth extinction arrived, and this time, every trilobite disappeared. Not reduced, not pushed to the margins, gone. How does a creature survive almost everything Earth can throw at it, only to vanish in the end? In today's journey, we're tracing the rise of one of the most successful animals that ever lived, the strange world it inhabited, and the catastrophe that finally brought its long reign to an end. If this is your kind of thing, hit like and subscribe. It costs nothing, and it keeps this channel going. And drop a comment below. Are you watching this winding down for the night, or watching this during your active day? Now, let's begin. Imagine tracing the history of life backward until familiar creatures disappear one by one. Fish vanish, corals vanish, shells vanish. Continue further, and the ocean itself begins to feel unfamiliar. Around 541 million years ago, much of the seafloor was covered by sprawling microbial mats, living layers of bacteria and algae that stretched across the sediment like a planetary skin. For immense spans of time, these communities shaped the character of marine environments while facing relatively little disturbance from animal life. The organisms inhabiting this world belonged largely to a chapter known as the Ediacaran. Their bodies lacked many of the features that would later become commonplace. Fossils reveal flattened forms, quilted patterns, and branching shapes that seem almost detached from modern biology. Many appear to have possessed neither obvious mouths nor recognizable heads. Evidence for complex sensory organs is absent. They occupied a biosphere where movement was limited, interactions were comparatively simple, and vision had not yet become a driving force in survival. Then the fossil record changes with startling speed. Across roughly 20 million years, a brief interval by geological standards, new body plans appear in abundance, limbs emerge, hard skeletons become common, burrowing animals churn sediments that had remained largely undisturbed for ages. Predation becomes a defining ecological pressure. Paleontologists refer to this interval as the Cambrian explosion because evolutionary innovation seems to burst into view across the planet's oceans. A striking aspect of this transformation is that many developments arrived together. Armor offered protection, mobility improved, feeding strategies diversified. Organisms began interacting with one another in increasingly sophisticated ways. Every adaptation created fresh opportunities while imposing fresh challenges. Life entered a period of escalating ecological complexity, where success depended not only on surviving the environment, but also on responding to other living creatures. Among the ideas proposed to explain this transition, one carries an unusual elegance. The light switch hypothesis, introduced by Andrew Parker, suggests that the appearance of advanced vision may have altered the trajectory of evolution itself. Before image forming eyes evolved, animals could detect chemicals, water movement, or physical contact. Detailed visual information remained beyond reach. Once organisms gained the ability to form images of their surroundings, entirely new evolutionary possibilities emerged. A hunter capable of spotting prey from a distance gained a powerful advantage. Potential prey benefited from detecting danger before direct contact occurred. Camouflage became useful. Rapid movement acquired greater value. Body shape, coloration, and behavior could all influence survival in ways previously impossible. Evolutionary pressure intensified across countless species simultaneously, creating feedback loops that encouraged further innovation. This idea remains debated among scientists, since many factors likely contributed to the Cambrian explosion. Environmental change, rising oxygen levels, genetic developments, and ecological interactions all played important roles. Even so, vision occupies a unique position because it transformed information itself into a biological resource. The world became richer in signals, opportunities, and threats the moment animals could perceive it in greater detail. Among the earliest creatures associated with this visual revolution were the trilobites. Their appearance coincided with a period when ecosystems were being rewritten from the seafloor upward. Fossils preserve evidence of sophisticated eyes at a remarkably early stage in animal history. Those eyes belonged to animals that would eventually spread across the globe and endure for hundreds of millions of years. In that changing Cambrian world, the rise of the trilobites may have been more than a consequence of evolutionary change. It may have been one of its engines. A beam of sunlight entering Paleozoic seawater faced an unusual destination. Instead of passing through tissue shaped from proteins, it sometimes traveled into crystal. There, within a structure assembled by a trilobite hundreds of millions of years before mammals appeared, light followed pathways determined by the geometry of mineral itself. Few biological innovations are as strange, and none are known to have been used on such a scale. Trilobite eyes belong to a category known as compound eyes. Rather than forming a single image through one lens, they consisted of many visual units called ommatidia. Each unit possessed its own lens and gathered information from a small portion of the surrounding world. Modern insects and crustaceans employ the same general principle. A trilobite looking across the seafloor perceived its environment through thousands of individual sampling points woven together into a larger visual picture. The similarity ends at the lens. Nearly every animal that has ever evolved vision relies on transparent proteins to focus incoming light. Such lenses can grow, change shape, and adapt to different optical demands. Trilobites followed an entirely different route. Their lenses were composed of calcite, a transparent mineral made of calcium carbonate. The material was hard, rigid, and incapable of flexing. What appears at first glance to be an impossible choice became the foundation of one of evolution's most elegant engineering achievements. Calcite presents a serious optical challenge. It is birefringent, meaning that incoming light can split into separate rays as it travels through the crystal. Left uncorrected, this effect creates blurred and distorted images. Trilobites overcame the problem through extraordinary precision. The crystal structure of each lens was aligned so that its optical axis pointed directly along the path of incoming light. By controlling orientation with remarkable accuracy, distortion could be greatly reduced within the viewing angle that mattered most. Some trilobites carried this solution even further. Members of the group Phacopoda evolved lenses with two distinct optical layers. The upper portion consisted of calcite, while the lower portion incorporated chitin, an organic material also found in the exoskeletons of many arthropods. Together, these layers formed a doublet lens capable of correcting spherical aberration, a flaw that causes light entering near the edge of a lens to focus differently from light entering near its center. The significance of this design remained unrecognized until the 20th century. Physicist Riccardo Levisetti, a lifelong collector of trilobite fossils, attended a lecture by paleontologist Ewan Clarkson and noticed something extraordinary. The lens geometry preserved in trilobite eyes closely matched solutions later developed by human scientists. One corresponded to principles associated with René Descartes in 1637. Another resembled work published by Christian Huygens in 1690. Evolution had arrived at comparable optical answers hundreds of millions of years earlier. Because these lenses were mineral from the beginning, they fossilized with exceptional fidelity. Researchers can examine structures that interacted with sunlight more than half a billion years ago and still analyze their optical properties. Richard Forte described this achievement as a fiendishly clever exploitation of calcite's unusual characteristics. Across the immense history of life, only the brittle star is known to use calcite lenses today. The trilobite approach remains one of biology's rarest experiments, preserved not in memory, but in stone. A collector opening drawers of trilobite fossils for the first time often encounters a strange impression. The labels all carry the same name, yet the specimens seem to belong to entirely different worlds. One resembles a smooth oval shield resting against stone. Another bristles with spikes extending in every direction. A third carries towering eyes, sweeping horns, or a shape so unusual that its relationship to the others appears almost impossible. The diversity contained within the trilobites is one of the most extraordinary stories in the history of animal life. More than 20,000 species have been formally described, organized into 10 orders, over 150 families, and roughly 5,000 genera. New species continue to be identified from rocks around the world, suggesting that the true number was even greater. Across their immense span of existence, trilobites diversified into forms that occupied nearly every marine environment available to arthropods. Their sizes alone reveal the breadth of this expansion. Some species measured less than a millimeter in length, small enough to rest comfortably on a fingertip. At the opposite extreme stood giants such as Isotellus rex, reaching approximately 72 centimeters. Between those limits existed an astonishing range of body proportions, each reflecting a different way of living within Paleozoic seas. Despite this variation, every trilobite shared a common architectural framework. The body was divided lengthwise into three lobes, a central axial lobe flanked by two pleural lobes. This arrangement inspired the name trilobite itself. From front to back, the body consisted of the cephalon, or head, the thorax, formed from articulated segments, and the pygidium, the tail section. Evolution repeatedly modified this blueprint without abandoning it, producing a level of diversity comparable to countless designs emerging from the same set of engineering principles. Thoracic segments varied dramatically among groups. Some species possessed only a handful, while others carried more than 40. Segment number influenced flexibility, movement, and enrollment capability. Head structures displayed equal variety. Broad cephalic shields suited some lifestyles, while narrow wedge-shaped forms suited others. The glabella, the raised central region of the head, differed greatly in shape and size, often reflecting feeding behavior and internal anatomy. Vision also varied across this kingdom of forms. Certain trilobites developed enormous eyes that occupied much of the cephalon, granting wide fields of view within illuminated waters. Other species abandoned sight altogether. Fossils from deep water or sediment dwelling environments reveal lineages in which eyes were reduced or absent, indicating that natural selection shaped sensory systems according to habitat rather than following a single evolutionary path. Surface ornamentation transformed many trilobites into some of the most elaborate creatures of the Paleozoic. Spines projected from heads, thoraxes, and tails. Horn like structures curved outward in dramatic patterns. Some forms appear almost sculptural, their exoskeletons carrying projections whose purposes may have included defense, stabilization, camouflage, or display. Others retained smooth outlines suited to movement across soft seafloors. From equatorial waters to polar regions, from shallow continental shelves to darker depths, trilobites occupied ecological roles with extraordinary flexibility. Few animal groups have explored such a wide range of possibilities while retaining a recognizable body plan. Their success was not built upon a single form perfected over time. It emerged from thousands upon thousands of experiments unfolding across hundreds of millions of years. A trilobite crossing a stretch of Paleozoic seafloor might appear familiar at first glance. Its segmented body moved close to the sediment, its legs carrying it across mud that had accumulated grain by grain over countless years. For generations, this image shaped popular understanding of trilobites. The reality was far richer. The name trilobite describes an immense collection of species whose daily lives unfolded in dramatically different ways across the world's oceans. Many spent their lives processing sediment. These deposit feeders moved through mud and sand, consuming organic material mixed within the seafloor. Every mouthful contained fragments of decaying organisms, microbial matter, and nutrients trapped within the sediment. As they fed, they recycled material back into the ecosystem, functioning as an important link in the circulation of energy through marine communities. Other species specialized in scavenging. Carcasses sinking through the water eventually reached the seabed, where they became valuable resources. Trilobites feeding on this material helped break down organic remains before bacteria and other decomposers completed the process. Their activity returned nutrients to circulation and prevented food resources from remaining concentrated in a single location for long periods. Not every trilobite searched for food along the bottom. Certain forms appear to have filtered tiny particles directly from the water. Specialized appendages likely captured plankton and suspended organic matter drifting on currents. In productive seas filled with microscopic life, this strategy provided access to a steady food supply without requiring pursuit or excavation. Evidence also points toward active hunters. Some trilobites possessed body shapes and appendages suited for capturing small animals. Worms, tiny arthropods, and other invertebrates formed part of a dynamic food web where trilobites occupied multiple trophic levels. They were not merely prey or recyclers. In many environments, they participated directly in predatory interactions, contributing to the increasingly complex ecological relationships that characterized Paleozoic oceans. A number of species ventured away from the seafloor altogether. Streamlined bodies and enlarged eyes suggest lifestyles spent swimming through open water. These pelagic trilobites experienced a very different world from their bottom dwelling relatives. Instead of navigating sediments and burrows, they moved through water columns where visibility, currents, and plankton distributions shaped daily survival. Life within the sediment offered another path. Several lineages evolved reduced eyesight or lost vision entirely. Fossils indicate that these trilobites inhabited environments where light played little role. Burrowing through the substrate provided access to buried organic matter while reducing exposure to predators above. Their world was defined by touch, movement, and chemical cues carried through the sediment. Understanding these lifestyles remained difficult for many years because the most informative structures rarely fossilized. Trilobite legs, gills, and mouth parts consisted of softer tissues that were usually lost before preservation could occur. A major breakthrough arrived in 2024 with the discovery often called the Pompeii trilobites from Morocco's High Atlas region. Exceptional preservation revealed the underside of these animals in unprecedented detail. The fossils showed paired jointed limbs extending along the body, each branch serving a different function. One branch assisted with walking, while another carried feathery structures involved in respiration. Around the mouth sat clustered appendages, armed with dense inward facing spines. Their arrangement bears a striking resemblance to feeding mechanisms seen in modern horseshoe crabs. Together, these discoveries reveal a simple truth. Trilobites were never one kind of animal living one kind of life. They were an entire evolutionary society of specialists, each adapted to a particular way of making a living in the sea. A trilobite shell can tell a story long after the animal itself is gone. Some fossils bear scars, repaired fractures, and irregular grooves where damaged armor healed during life. These marks are among the oldest records of survival ever discovered. They reveal a world where danger had become a daily reality and where evolution was beginning one of its most influential competitions. Early Cambrian trilobites lived during a period when complex ecosystems were still taking shape. Species such as Olanellus possessed relatively thin exoskeletons and limited defensive options. Their undersides remained vulnerable, and many lacked the elaborate protective structures that would later characterize their descendants. Oceans were becoming more crowded, interactions more intense, and new predators were emerging with capabilities unseen in earlier chapters of life's history. Among the most famous was Anomalocaris, a swimming hunter reaching lengths of about 1 meter. Its body moved through the water with remarkable efficiency, propelled by rows of lateral flaps that rippled in sequence. At the front sat large compound eyes containing more than 16,000 lenses, granting visual abilities unprecedented for the time. Curved appendages, lined with spines extended forward, ready to seize passing prey. Within Cambrian seas, few creatures matched its combination of mobility and sensory power. For many years, Anomalocaris was imagined as a shell-crushing terror that fed extensively on trilobites. Recent studies suggest a more complicated picture. Biomechanical analyses indicate that its grasping limbs were better suited for capturing softer animals than breaking heavily mineralized armor. Even so, its presence altered the ecological landscape. Predators did not need to consume trilobites exclusively to influence their evolution. The threat of attack alone could shape the future of an entire lineage. Evidence preserved within fossils shows that attacks occurred. Certain trilobite specimens display healed injuries where sections of the exoskeleton had been damaged and later regenerated. These individuals survived encounters with predators and carried the record of those encounters for the rest of their lives. Every scar represented selective pressure acting on populations across millions of years. Responses appeared gradually. Exoskeletons became thicker and more strongly reinforced with mineral material. Armor that once served primarily structural purposes increasingly functioned as protection. Some lineages developed more elaborate defensive features, extending spines from various regions of the body. These projections may have made handling more difficult for predators, while also assisting with stability in moving water. One innovation proved especially important. Trilobites evolved the ability to enroll, folding the body into a compact ball that shielded vulnerable soft tissues. Early versions of this behavior remained imperfect. Small openings persisted between segments, leaving weak points exposed. Through successive generations, anatomical refinements produced intricate interlocking mechanisms that reduced these gaps. The enrolled trilobite became a living fortress, presenting little beyond hardened armor to an attacker. Vision participated in this contest as well. Eye placement shifted in some groups, while visual coverage expanded in others. Detecting movement sooner increased the likelihood of escape or defensive response. Across the ocean floor, information became a survival tool every bit as valuable as armor. The pattern established during this period would echo throughout the history of life. Predators improved, prey adapted. Each advance created opportunities for another response. In the Cambrian oceans, trilobites stood at the center of this process, helping shape one of Earth's earliest and most enduring evolutionary rivalries. Recovery can sometimes be more transformative than survival itself. The lineages that emerged from the end Cambrian extinction entered a world filled with opportunity. Many competitors had disappeared. Ecological space stood open across broad regions of the ocean. From those surviving trilobite populations came one of the most spectacular radiations in the history of marine life. Throughout the Ordovician period, trilobites diversified at an extraordinary pace. New species appeared across continental shelves, offshore environments, reef systems, and deeper waters. Groups that had endured the losses of the previous extinction expanded into niches left vacant by vanished organisms. The result was a flourishing of forms unlike anything seen before. By this point, trilobites were no longer participants in Paleozoic ecosystems. They had become one of their defining features. The oceans themselves encouraged this expansion. Extensive shallow seas covered large portions of the continents, creating productive marine habitats rich in food and ecological variety. Brachiopods spread across the seafloor. Bryozoan colonies formed intricate structures that added complexity to marine landscapes. Echinoderms diversified into numerous forms. Graptolites drifted through the water column. Each group contributed to an increasingly interconnected web of life, and trilobites occupied positions throughout it. Within this flourishing world, body size reached impressive extremes. Among the most famous examples is Isodolus rex, the largest trilobite ever discovered. Found along the shores of Hudson Bay in northern Manitoba, Canada, the specimen measured approximately 72 centimeters in length and 40 centimeters in width. For an animal belonging to a group often associated with modest dimensions, the scale is striking. The discovery itself became an important moment in trilobite research. A team from the Royal Ontario Museum, including Dave Rudkin, Robert Elias, Graham Young, and Edward Dobrzhansky, recovered a specimen that was nearly complete and fully articulated. Such preservation is uncommon for trilobites of any size. Fossils are frequently fragmented by scavengers, currents, burial processes, or geological activity. Finding an individual preserved almost intact offered an unusually clear glimpse into one of the giants of the Ordovician seas. When formally described in 2003, Isotellus rex exceeded the length of the largest previously known complete trilobite by roughly 70%. Researchers noted that it ranked among the largest arthropods ever documented. Its immense size likely reflected environmental conditions associated with warm, productive, shallow seas located near equatorial regions. Similar patterns appear elsewhere in the fossil record, where favorable climates and abundant resources support unusually large body sizes. The Ordovician was not defined solely by giants. Across the trilobite family tree, diversity expanded in nearly every direction. Species differed in feeding strategies, habitat preferences, body architecture, and sensory adaptations. The group reached levels of ecological versatility unmatched in its earlier history. Oceans that once contained recovering populations now hosted thriving communities composed of countless specialized forms. Viewed from within that moment, the future would have appeared secure. Trilobites occupied an enormous geographic range and displayed extraordinary adaptability. Their success seemed deeply rooted in the structure of Paleozoic ecosystems, yet patterns, visible only across immense spans of time, were already beginning to emerge. Recovery followed extinction, diversity followed recovery, but each cycle subtly altered the composition of the group. The Ordovician represented the height of trilobite prosperity, a period when their evolutionary empire stretched farther than ever before across the living seas of Earth. Success can create the illusion of permanence. Across the Ordovician world, trilobites occupied an extraordinary range of habitats and lifestyles. Their species filled shallow seas stretching across broad continental shelves, and their presence seemed woven into the structure of marine ecosystems themselves. Then the planet began to change in ways no adaptation could fully anticipate. Around 445 million years ago, Earth entered the first of the events now known as the Big Five mass extinctions. The transformation unfolded on a planetary scale. Climate patterns shifted toward intense cooling, and massive ice sheets expanded across Gondwana, the southern supercontinent. As growing glaciers locked enormous volumes of water onto land, sea levels fell dramatically. Coastlines retreated. Shallow marine environments that had supported abundant life for millions of years began to disappear. For trilobites, this was especially significant because many species depended on continental shelf habitats. These regions combined sunlight, nutrients, and ecological complexity in ways that encouraged biodiversity. As the water withdrew, entire communities lost the environments upon which they relied. Species adapted to warm, shallow settings found themselves facing shrinking ranges and increasingly unstable conditions. The extinction did not arrive as a single blow. Geological evidence indicates two major pulses separated by a period of environmental transition. The first phase was driven largely by cooling temperatures and habitat loss associated with falling sea levels. Organisms that could not tolerate the new conditions vanished from large portions of the globe. Marine ecosystems contracted as environmental pressures intensified. A second crisis followed when climatic conditions shifted again. Glaciers eventually melted, returning vast quantities of water to the oceans. This recovery carried its own consequences. Deep waters, depleted in oxygen, spread across continental shelves, bringing anoxic conditions into regions where many marine organisms lived. Habitats that had survived the first pulse now faced a different challenge. Species already weakened by environmental disruption encountered another wave of stress before recovery could fully begin. The scale of loss was immense. Approximately 85% of marine species disappeared. Entire evolutionary lineages ended. Communities that had taken millions of years to assemble were transformed in geological moments. Trilobites suffered heavily during this upheaval. Numerous families and genera vanished, particularly those specialized for warm shelf environments. Diversity declined sharply across many branches of the trilobite family tree. Even the giants were not spared. The lineage that produced Isotellus, among the largest trilobites ever known, failed to cross the Ordovician boundary. Physical size, evolutionary success, and geographic distribution offered no guarantee of survival. Extinction operated according to environmental realities rather than prestige within the fossil record. Those that endured tended to share certain characteristics. Many occupied deeper or cooler waters where environmental fluctuations proved less severe. Others possessed broader ecological tolerances, allowing them to persist under changing conditions. Generalists often fare better during periods of instability because flexibility provides options when familiar circumstances disappear. When the crisis finally eased, trilobites remained part of Earth's story. Their numbers were reduced, their diversity diminished, and many celebrated lineages were gone forever. Yet the group itself survived. That achievement mattered. A pattern had begun to emerge, one that would define much of trilobite history. Catastrophe arrived, diversity contracted, and a remnant persisted. The first great test had reshaped their world, but it had not erased them from it. Extinction leaves gaps that are not immediately visible. Species disappear, ecosystems reorganize, and the survivors continue forward, carrying the consequences of what was lost. By the beginning of the Silurian period, roughly 444 million years ago, the oceans were entering such a phase. Life persisted, communities endured, and evolutionary activity resumed. Yet, the world emerging from the end Ordovician crisis was not identical to the one that had existed before it. Trilobites participated in this rebuilding effort. New species appeared across recovering marine environments, and several lineages expanded into opportunities created by the extinction. Diversity increased from its post-crisis low point, restoring some of the richness that had characterized earlier ages. The recovery was genuine, but it never fully recreated the extraordinary breadth achieved during the Ordovician peak. Certain branches of the trilobite family tree were gone forever, leaving spaces that could not be refilled. Among the groups that flourished during this interval were the Phacopoda and Lichida. Their fossils reveal bodies shaped by a world where survival demanded stronger defenses. Exoskeletons became more substantial. Enrollment mechanisms improved, allowing individuals to seal themselves more effectively against attack. Spines grew longer and more elaborate in many species, transforming portions of the trilobite fauna into some of the most ornate arthropods of the Paleozoic. The oceans surrounding them were also changing. Coral reef systems expanded and became increasingly important centers of biodiversity. Brachiopod communities recovered across broad continental shelves. Crinoids, mollusks, and numerous other groups contributed to marine ecosystems of growing complexity. Food webs developed new layers of interaction, creating environments rich in ecological possibilities. Within these ecosystems, trilobites remained successful participants. They occupied numerous habitats and continued to display impressive adaptability. Their role, however, had shifted in subtle ways. During earlier periods, trilobites often stood among the most dominant arthropods in marine environments. In the Silurian, they shared that stage with an expanding cast of competitors whose influence was steadily increasing. Among those competitors were the Eurypterids, often called sea scorpions. Some species reached formidable sizes and occupied ecological positions that overlapped with trilobite lifestyles. Other arthropod groups also diversified, creating a more crowded evolutionary landscape. Opportunities that had once belonged almost exclusively to trilobites were now contested by multiple lineages pursuing similar resources. Changes were unfolding beyond the oceans as well. Along shorelines and damp terrestrial environments, the earliest plants were establishing themselves on land. Their appearance marked the beginning of a transformation that would eventually alter weathering rates, nutrient cycles, atmospheric composition, and patterns of sediment transport. The consequences would take millions of years to fully unfold, yet the foundations were already being laid during the Silurian. Viewed through the lens of survival, the period was encouraging. Trilobites had endured a major extinction and rebuilt significant portions of their diversity. Many lineages remained widespread and successful. Their fossil record from this interval demonstrates resilience, adaptability, and continued evolutionary creativity. Viewed through a longer lens, another pattern becomes visible. The recovery reached only partway toward former heights. Diversity returned, though not completely. Ecological influence remained substantial, though no longer unrivaled. The Silurian preserved a delicate balance between renewal and reduction. Trilobites had weathered their first great catastrophe and emerged on the other side, still thriving, yet carrying subtle signs that each future recovery might restore a little less than the one before. A new kind of hunter entered the oceans during the Devonian. Trilobites had spent tens of millions of years adapting to threats from other arthropods and invertebrates, refining armor, improving enrollment, and developing increasingly sophisticated sensory systems. The challenges ahead would come from a very different direction. Animals with internal skeletons, powerful muscles, and articulated jaws were beginning to transform marine ecosystems. The Devonian period, spanning from roughly 419 million to 359 million years ago, is known as the Age of Fish because vertebrates diversified on an extraordinary scale. Armored placoderms patrolled coastal waters. Early sharks expanded into new environments. Primitive bony fishes multiplied across reefs, lagoons, and continental shelves. Marine communities that had once been shaped primarily by invertebrates now contained predators capable of pursuing prey with unprecedented speed and force. Among the most famous was Dunkleosteus, a giant placoderm whose head and jaws were enclosed in thick bony plates. Instead of conventional teeth, it possessed sharpened bone structures capable of generating immense biting power. Fossil evidence suggests that some large placoderms occupied positions near the top of food webs. Their arrival introduced a form of predation unfamiliar to earlier trilobite generations. A shell that could withstand grasping appendages or crushing pressure from many invertebrates faced a different challenge when confronted with jaws designed to shear, crack, and slice. Defensive strategies that had served trilobites well during earlier periods were no longer guaranteed protection. Evolutionary innovations that once provided an advantage now existed within an environment where predators themselves were evolving rapidly. At the same time, trilobites were producing some of the most extraordinary forms in their long history. Devonian fossils reveal species adorned with structures that appear almost fantastical. Wallazeurops carried a three-pronged projection extending from the front of its head. Urbanochile developed towering eyes elevated on vertical columns. Dicranurus displayed sweeping spines, curving outward like elaborate horns. These creatures demonstrate how much variation could emerge from the trilobite body plan after hundreds of millions of years of experimentation. Such diversity reflected successful adaptation to particular ecological circumstances. Natural selection can produce highly specialized organisms when environments remain stable for long periods. Features that improve feeding, defense, reproduction, or sensory performance become refined across countless generations. Specialization often creates impressive biological designs, though it can also reduce flexibility when conditions begin to shift. Devonian reef systems rank among the most complex ecosystems of the Paleozoic. Coral communities expanded across warm seas, creating intricate habitats filled with fish, mollusks, echinoderms, crustaceans, and countless smaller organisms. Competition intensified as more groups occupied overlapping ecological roles. Space, food, and shelter became resources contested by a growing diversity of life. Within these environments, trilobites remained present and continued evolving. Their fossil record demonstrates persistence rather than sudden collapse, yet broad trends suggest that the balance was changing. Vertebrate predators increased in abundance. Alternative arthropod groups expanded. Ecological opportunities available to trilobites became narrower than they had been during earlier ages. Across millions of years, the shift was gradual enough that no single generation would have recognized it. Reef communities still contained trilobites, and many species remained successful. Looking back through the fossil record, however, a pattern becomes visible. The Devonian was an age of spectacular innovation, but it was also an age in which trilobites found themselves sharing their world with rivals that were becoming faster, stronger, and increasingly dominant within the oceans they had once helped define. Some crises arrive as a single moment, others unfold so gradually that entire ecosystems spend millions of years living through them. The late Devonian extinction belonged to the second category. It was not one catastrophe, but a sequence of disruptions spread across immense stretches of geological time, each one removing pieces of the living world until the cumulative damage became impossible to reverse. Several major extinction pulses mark this interval. Among them were the Taganic event, the Kellwasser events between roughly 375 and 372 million years ago, and the Hangenberg event near the close of the Devonian. Between these episodes, life continued, adapted, and diversified in some regions. Yet every recovery was interrupted by another wave of environmental instability. Scientists continue to debate the exact combination of causes. Evidence points toward a complicated interaction of volcanic activity, changing sea levels, climatic fluctuations, and widespread oxygen depletion in marine environments. Another possibility begins far from the ocean itself. Plants had been spreading across the continents for millions of years, sending roots into rock and soil. This biological expansion accelerated weathering processes, releasing nutrients that rivers carried toward the sea. Increased nutrient input may have fueled enormous algal blooms which, upon decomposition, consumed oxygen and contributed to expanding dead zones. Regardless of the precise mechanism, marine ecosystems faced recurring stress. Reef communities suffered severe losses. Many groups that had flourished throughout the Devonian declined sharply or disappeared altogether. Organisms adapted to stable environmental conditions found themselves confronting a world that repeatedly shifted beneath them. For trilobites, the consequences proved more severe than any previous challenge. Earlier extinctions had reduced diversity while leaving multiple lineages available for recovery. The late Devonian crisis cut much deeper. Entire branches of the trilobite family tree vanished. Groups that had survived for tens of millions of years, including some of the most distinctive forms ever produced, disappeared from the fossil record. The casualties included species adorned with spectacular anatomical innovations. The trident-bearing Wallaceraps, the towering-eyed Urbanochili, and countless spine-covered relatives belonged to evolutionary experiments that had unfolded across vast spans of time. Their disappearance marked the end of a remarkable chapter in trilobite history. Features shaped by millions of generations ceased to exist, preserved only in stone. By the conclusion of the Devonian, the scale of loss becomes difficult to overstate. Every trilobite order, except one, had been eliminated. A lineage that once contained extraordinary ecological and anatomical diversity was reduced to a single surviving branch. The comparison is startling. It would be as though nearly all major groups of modern mammals vanished, while one small remnant carried the entire future of the class. The survivors belonged to the order Proetida. They lacked the dramatic ornamentation that characterized many Devonian relatives. Their bodies were generally smaller, their forms less elaborate, and their lifestyles comparatively unassuming. In a world where specialization had often produced astonishing biological designs, persistence now rested with organisms that occupied a more modest position within marine ecosystems. The Devonian ended with trilobites still present, yet profoundly transformed. The age of towering eyes, extravagant spines, and spectacular experimentation had drawn to a close. What remained was a reduced lineage carrying the legacy of a group that had once dominated oceans across the globe. Survival had been achieved once again, though the cost was greater than ever before, and the space available for future recovery had become dramatically smaller. Survival often leaves behind a misleading picture. Looking at the fossil record after the late Devonian extinction, one might imagine the remaining trilobites as the strongest, largest, or most advanced representatives of their lineage. The evidence suggests something very different. The group that carried trilobites into the next chapter of Earth's history was comparatively modest, composed of animals that would have attracted little attention beside the spectacular forms that had vanished. These survivors belonged to the order Proetida. Most species were small, measuring only a few centimeters in length. Their bodies were compact and efficient. They lacked the towering visual structures, extravagant spines, and elaborate projections that had characterized many Devonian trilobites. In museums and fossil collections, they rarely command the same fascination as their more dramatic relatives. Their appearance reflected practicality more than display. Exactly why the Proetida survived remains uncertain. Paleontology often reveals patterns more clearly than precise causes. Several possibilities have been proposed. Smaller body size may have reduced resource requirements during periods of environmental stress. Generalist feeding habits could have allowed these trilobites to exploit a broader range of food sources when ecosystems became unstable. Greater tolerance for changing conditions may have helped them persist where specialists failed. Habitat distribution might also have played a role, placing some populations in regions less severely affected by extinction pressures. No single explanation has gained universal acceptance. Survival is frequently shaped by a combination of biological traits and circumstance. Two closely related species can experience very different outcomes depending on where they live when environmental disruption begins. Extinction does not always reward the most impressive organisms. It often favors those capable of enduring uncertainty. This pattern appears repeatedly throughout the history of life. Following major extinction events, the survivors are commonly ecological generalists. They tend to occupy broad niches, consume varied resources, and tolerate a wider range of environmental conditions. Highly specialized organisms can thrive during stable periods, yet specialization may become a burden when habitats transform rapidly. Flexibility often proves more valuable than perfection. The Proetida fit this pattern with striking precision. Their anatomy lacked extreme adaptations tied to narrow ecological roles. They appear to have occupied lifestyles that remained viable across diverse settings. While many famous trilobite groups evolved increasingly specialized forms, The Proatida retained a comparatively conservative design. That restraint may have become their greatest advantage. Their survival carried enormous consequences. Earlier extinctions had reduced trilobite diversity while leaving multiple orders available for recovery and diversification. The late Devonian crisis produced a very different outcome. Once the extinction ended, the Proatida stood alone. Every other trilobite order had disappeared. Hundreds of millions of years of evolutionary branching had narrowed to a single remaining lineage. From that point onward, the future of the entire trilobite class rested upon one group. Every species that would live during the Carboniferous and Permian descended from Proetidan ancestors. Every adaptation, migration, success, and decline would occur within the boundaries of this surviving branch. The evolutionary possibilities available to trilobites had become dramatically smaller. Their persistence remains impressive. The lineage had already survived multiple global crises and continued onward despite overwhelming losses. Yet the nature of survival had changed. Earlier recoveries began with diverse foundations capable of generating new forms. The Proetida inherited a far narrower starting point. They carried the weight of an entire lineage alone, preserving the final thread of a story that had already stretched across hundreds of millions of years. The world above sea level was becoming increasingly unfamiliar. Forests spread across vast lowlands, giant insects moved through dense vegetation, and early vertebrates expanded their presence on land. These transformations would eventually reshape the future of life on Earth. Far offshore, another story was unfolding, one less dramatic in appearance, but equally significant. The trilobites were still present, still surviving, yet their role in the oceans had changed profoundly. The Carboniferous period began around 359 million years ago, following the devastation of the late Devonian crises. Only the Proetida remained. From that narrow foundation, a modest recovery took place. New species emerged, populations expanded into suitable habitats, and trilobites maintained a geographic distribution that stretched across multiple regions of the globe. Judged solely by survival, the outcome appeared encouraging. A closer look reveals a different picture. The recovery never approached the scale of earlier rebounds. During the Ordovician, trilobites diversified into thousands of forms, occupying a remarkable variety of ecological roles. Carboniferous trilobites existed within far narrower boundaries. Their diversity increased somewhat during the early part of the period, yet the overall range of forms remained limited compared with the richness that had once characterized the group. Marine ecosystems themselves were becoming increasingly crowded. Crinoids flourished in many environments, covering portions of the seafloor with dense communities of stalked filter feeders. Brachiopods remained abundant across continental shelves. Coral ecosystems continued to contribute structural complexity to marine habitats. Fish diversified into forms occupying a growing range of ecological positions. The oceans were productive, dynamic, and biologically rich. Within this environment, trilobites no longer occupied center stage. They remained participants in marine communities, though their influence had diminished. Ecological roles once associated with trilobites were increasingly filled by other organisms. Crustaceans diversified alongside fish and expanded into habitats where trilobites had previously prospered. Competition for resources became part of a broader evolutionary landscape populated by groups that were themselves adapting and expanding. The fossil record captures this transition with unusual clarity. Trilobites did not disappear from Carboniferous rocks. Their fossils remain widespread enough to demonstrate continued success in certain settings. Yet, diversity stayed persistently low compared with earlier periods. The contrast is striking. A lineage that once generated extraordinary anatomical variety now persisted through a relatively small collection of species and genera. Survival alone can conceal long term decline. A group may remain geographically widespread while gradually losing ecological significance. That pattern appears repeatedly in Earth's history. Carboniferous trilobites provide a particularly clear example. They endured environmental change, maintained viable populations, and continued reproducing across millions of years. At the same time, the evolutionary momentum that once drove their expansion had largely faded. Each succeeding interval brought subtle reductions. Species counts remained modest. Habitat ranges became more restricted in many regions. Opportunities for diversification appeared fewer than before. The trend was gradual enough that no single moment marked a decisive turning point. Instead, the decline unfolded across immense spans of time, visible only when viewed through the broader perspective provided by geology. Even so, persistence deserves recognition. Few lineages survive multiple mass extinctions and continue onward for tens of millions of years afterward. The Proetida accomplished exactly that. They carried the trilobite legacy through a changing world, maintaining a presence in oceans that no longer resembled those of their ancestors. Their story during the Carboniferous was neither triumph nor catastrophe. It was endurance sustained across millions of years while the evolutionary spotlight increasingly shifted elsewhere. Maps of the Permian world would have looked unlike anything familiar today. Continents that had once drifted separately across the planet gradually converged until nearly all major landmasses became joined together. The result was Pangaea, a supercontinent stretching across enormous distances, reshaping weather patterns, coastlines, oceans, and the conditions upon which countless species depended. For trilobites, this planetary rearrangement created pressures that accumulated across millions of years. Marine life has always depended heavily on shallow continental shelves. These broad, sunlit regions support rich ecosystems because nutrients circulate efficiently, sunlight reaches the seafloor, and environmental conditions often remain suitable for a wide variety of organisms. Throughout much of their history, trilobites thrived in precisely these settings. Generation after generation occupied coastal seas, shelf environments, and marine habitats connected to the margins of continents. As Pangaea assembled, those favorable environments began to shrink. Separate continental blocks carried extensive coastlines, creating long stretches of shallow marine habitat. When those landmasses fused together, the total length of coastline declined substantially. A reduction in coastline meant a reduction in continental shelf area. Across the globe, many of the environments that had supported marine diversity for hundreds of millions of years became less extensive. Changes were not limited to geography. Large inland seas that once covered portions of the continents gradually disappeared. Regions far from the ocean became increasingly dry as moisture struggled to penetrate deep into the continental interior. Climate patterns shifted. Habitats that had once connected marine populations became fragmented or vanished entirely. Species adapted to particular environmental conditions found themselves with fewer places to live. Ocean circulation also changed. Water movement plays a crucial role in distributing oxygen and nutrients through marine ecosystems. Alterations in continental arrangement can redirect currents, influence temperature patterns, and affect biological productivity. Evidence from Permian rocks suggests that some marine environments experienced increasingly challenging conditions as circulation patterns evolved. For organisms already facing habitat reduction, these changes added another layer of stress. The trilobites entered this period carrying the weight of earlier losses. Previous extinctions had removed entire branches of their evolutionary tree. Recovery had become progressively weaker after each crisis. By the Permian, only a small remnant remained. The extraordinary diversity that once included thousands of species had contracted to a tiny fraction of its former scale. Fossil evidence suggests that only a handful of genera survived into the later Permian. Estimates vary, yet the number was likely no more than a dozen or so. This decline becomes especially striking when compared with the group's earlier history. A lineage that had once occupied nearly every marine niche available to arthropods now persisted in scattered pockets of suitable habitat. Those final populations were concentrated in particular shallow shelf regions where environmental conditions remained favorable. Their geographic range was limited, their diversity was limited, their opportunities for expansion were limited. Survival remained possible, but resilience had diminished considerably. Earlier, trilobite communities could absorb losses because diversity itself provided stability. The remaining Proetida possessed far fewer options. Life continued. Individuals fed, molted, reproduced, and left descendants. Fossils from these final chapters show organisms still carrying the familiar body plan that had endured for hundreds of millions of years. Yet the broader situation had changed. The last trilobites occupied a narrowing corner of the marine world, dependent on habitats that were becoming increasingly vulnerable to disruption. Their lineage had not vanished, it had endured catastrophe after catastrophe. By the close of the Permian, however, there was little room left for recovery if another global crisis arrived. Far to the north of the Permian world, deep within the crust beneath what is now Siberia, forces that had been building for immense spans of time finally reached the surface. Cracks opened across the landscape. Magma surged upward through fractures stretching across enormous distances. What emerged was not a mountain-shaped volcano rising above the horizon, but something far larger and more destructive, a volcanic province whose eruptions would alter the course of life itself. Geologists call this event the Siberian Traps. The name comes from the stair-like layers of hardened basalt that remain today. Around 251.9 million years ago, those layers were not yet stone. They were rivers of molten rock spreading across the surface in eruption after eruption. Lava flooded outward over an area exceeding 2 million square kilometers. New flows arrived before older ones had fully cooled. The process continued for roughly 2 million years, creating one of the largest volcanic episodes known in Earth's history. The scale challenges ordinary comparison. Enough lava erupted to cover vast regions beneath tremendous thicknesses of basalt. Landscapes disappeared beneath molten rock. River systems vanished. Ecosystems that had existed for millions of years found themselves transformed into fields of fire and stone. Yet the lava itself represented only part of the danger unfolding across the planet. Each eruption released enormous quantities of gases into the atmosphere. Carbon dioxide poured upward in staggering amounts. Sulfur dioxide accompanied it, altering atmospheric chemistry and influencing climate systems. These emissions accumulated across thousands of generations, steadily changing conditions throughout the world. The atmosphere that surrounded Permian organisms was becoming fundamentally different from the one in which they had evolved. Another process amplified the crisis. Rising magma intruded into sedimentary layers rich in coal, hydrocarbons, and evaporite minerals. As these deposits heated, they released additional gases. Methane entered the atmosphere. Toxic compounds escaped from the crust. Carbon that had remained locked underground for immense periods suddenly became part of the planetary climate system. Temperatures began to climb. Oceans absorbed increasing amounts of heat. Climate zones shifted. Rainfall patterns changed across continents already affected by the assembly of Pangea. Regions adapted to one set of environmental conditions gradually found themselves living within another. Ecological communities that had developed over millions of years faced stresses from multiple directions at once. Marine ecosystems were especially vulnerable. Warm water holds less dissolved oxygen than cool water. As temperatures rose, oxygen availability in many marine environments declined. Ocean circulation patterns, already altered by continental rearrangement, struggled to distribute oxygen and nutrients effectively. Conditions became increasingly difficult for organisms dependent upon stable marine habitats. The remaining trilobites occupied a world that had little margin for disruption. Their diversity had been reduced repeatedly by earlier extinction events. Their geographic distribution had narrowed. Their populations persisted in scattered refuges along shrinking continental shelves. They had survived glaciations, sea level changes, ecological competition, and previous biological crises. Each survival left fewer branches on their evolutionary tree. Across the Permian seas, life continued its daily rhythms, while the foundations beneath those rhythms shifted. The first eruptions did not mark a single catastrophic moment. They marked the beginning of a drawn-out transformation of Earth's atmosphere, oceans, and climate. The planet was entering a crisis unlike any it had experienced since complex life first flourished, and the consequences were only beginning to unfold. A living ocean depends upon balance. Temperature, oxygen, acidity, and nutrient cycles interact continuously, creating conditions that allow countless organisms to survive. During the closing chapter of the Permian, that balance began to unravel. The volcanic forces already reshaping the atmosphere were now transforming the chemistry of the sea itself, turning one of Earth's richest ecosystems into an increasingly difficult place for life to endure. As carbon dioxide accumulated in the atmosphere, global temperatures continued to rise. The oceans absorbed much of that additional heat. Warm water behaves differently from cool water, especially when it comes to oxygen. Colder water can hold greater quantities of dissolved oxygen, while warmer water holds less. Across broad regions of the world, marine organisms found themselves living in water that contained progressively smaller oxygen reserves. Heat created another problem. Surface waters became warmer and lighter, while deeper waters remained colder and denser. Under ordinary conditions, ocean currents and seasonal mixing help transport oxygen downward. During the late Permian, that exchange weakened. Layers of water became increasingly isolated from one another. The surface and deep ocean no longer communicated as effectively as they once had. This process, known as stratification, had profound consequences. Oxygen consumed by organisms and natural decay in deeper waters was no longer replaced efficiently. Entire regions of the ocean gradually lost their oxygen supply. Scientists refer to these conditions as anoxia. In anoxic environments, many familiar forms of marine life struggle to survive. Habitats that had supported complex ecosystems for millions of years became biological dead zones. Another chemical shift unfolded at the same time. Oceans absorb carbon dioxide directly from the atmosphere. When carbon dioxide dissolves in seawater, it reacts to form carbonic acid. Increasing amounts of atmospheric carbon dioxide therefore caused seawater chemistry to change. The result was ocean acidification, a process that reduced the availability of carbonate ions needed by many organisms to construct shells and skeletal structures. For trilobites, this development struck at the core of their biology. Their exoskeletons contained substantial amounts of calcite, a mineral form of calcium carbonate. Throughout their lives, they repeatedly molted, shedding old armor and building new protective coverings. Each molt required access to the chemical ingredients necessary for mineralization. Acidified seawater made that process increasingly difficult. The challenge extended beyond individual growth. Juveniles attempting to construct their first exoskeletons faced greater obstacles. Adults recovering after molting encountered harsher conditions. Populations already reduced by earlier environmental pressures now had to contend with a world where the raw materials of their armor were becoming harder to obtain and maintain. Deep within oxygen-poor waters, another danger emerged. Certain bacteria thrive where oxygen is absent. These microorganisms produce hydrogen sulfide, a toxic gas harmful to many forms of life. Geological evidence suggests that hydrogen sulfide may have accumulated extensively during portions of the crisis. In some regions, it likely spread upward from deeper waters, contaminating habitats that had once supported diverse communities. Heat, oxygen loss, acidification, and toxic chemistry did not operate separately. They reinforced one another, creating a cascade of environmental stress across the globe. Marine ecosystems were attacked from multiple directions at once. Species capable of tolerating one challenge often faced several others simultaneously. By the height of the catastrophe, conditions across much of the ocean had become hostile on a scale rarely seen in Earth's history. The result was devastating. Nearly 95% of marine species disappeared, making this the most severe extinction event ever experienced by complex animal life. Near the end of the Permian, the trilobites existed as scattered remnants of a lineage that had once dominated the seas. Their story stretched back to the dawn of complex animal life, to oceans where eyes were new, predators were emerging, and evolutionary possibilities seemed limitless. Across roughly 270 million years, they had survived upheavals that erased countless other groups. What remained now was a small collection of species carrying the final thread of that immense history. Among the last representatives were members of genera such as Paraphilipsia, part of the surviving Proetida lineage that had endured the crises of the late Devonian. These animals occupied the shrinking marine environments still capable of supporting them. Their habitats were concentrated in relatively restricted, shallow water settings, fragments of a world that had become increasingly unstable. The broad geographic spread and ecological variety that once characterized trilobites had largely disappeared. Earlier in their history, diversity had provided resilience. During previous extinctions, losses in one region or ecological niche could be balanced by survival elsewhere. Multiple orders, hundreds of genera, and thousands of species created opportunities for recovery. New forms could emerge from surviving branches of the evolutionary tree. By the close of the Permian, those branches had already been cut away. Only a single order remained. This loss of diversity carried consequences beyond simple numbers. Evolutionary flexibility depends upon variation. A large and widespread group contains many different adaptations, lifestyles, and environmental tolerances. When conditions change, at least some members may possess traits that allow survival. The final trilobites no longer had that advantage. Their lineage had become narrow, concentrated, and vulnerable. As warming intensified and ocean chemistry shifted, the challenges multiplied. Oxygen levels declined across large portions of the marine realm. Acidification altered the chemical balance of seawater. Habitats contracted, ecological networks unraveled. Organisms that depended upon stable environmental conditions found fewer places where those conditions persisted. For trilobites, the composition of their exoskeletons added another burden. Calcite had served them extraordinarily well throughout their history. It provided durable armor, supported countless evolutionary innovations, and left behind fossils of remarkable quality. Through those mineralized remains, their story survived long after the animals themselves vanished. Yet the same calcite-rich structure became increasingly difficult to maintain in acidifying oceans. Molting had always been essential to trilobite life. Growth required the shedding of old exoskeletons and the construction of new ones. Under deteriorating chemical conditions, this process became more demanding. A biological strategy that had functioned successfully for hundreds of millions of years now faced environmental circumstances unlike those under which it evolved. The Great Dying did not arrive as an isolated blow directed solely at trilobites. It swept across entire ecosystems, removing species from nearly every branch of marine life. Trilobites entered the catastrophe, already diminished by a long sequence of setbacks. The extinction event served as the final closing act of a decline that had been unfolding for roughly 150 million years. When the extinction ended, the trilobites were gone. No surviving population remained in a distant basin. No hidden refuge preserved a final species. A lineage that had witnessed nearly the entire Paleozoic era disappeared completely. The seas continued. New groups rose to prominence, and Earth moved into another chapter of its history. The world that had shaped the trilobites and the world they had helped shape in return had passed away with them. A trilobite fossil usually tells its story through hard parts. Eyes remain, shells remain. The outlines of thoraxes and tails endure across immense spans of time. Reproduction leaves far fewer traces. Courtship, spawning, and mating behavior rarely fossilize, which left one of the most intimate parts of trilobite life concealed for generations of researchers. For much of paleontology's history, scientists could only make cautious inferences. Trilobites molted, grew, and spread across the world's oceans for hundreds of millions of years. So, reproduction clearly succeeded. The details, however, remained frustratingly elusive. Fossils revealed the results of life, yet the processes that produced new generations seemed to vanish before reaching the rock record. A breakthrough arrived from a damaged specimen. In 2022, researchers Sarah Lasso and Javier Ortega Hernandez published a study in the journal Geology describing an unusual fossil of Aulinoides serratus, a Cambrian trilobite that lived roughly 508 million years ago. The specimen preserved something unexpected within the middle region of the body. Two pairs of appendages differed noticeably from the surrounding limbs. They were smaller, modified, and positioned in a way that suggested a specialized function. The researchers interpreted these structures as claspers, appendages used by mature males during reproduction. Such limbs could have allowed a male trilobite to hold a female securely while eggs and sperm were released into the surrounding water. External fertilization is common among marine invertebrates, yet successful fertilization often requires close positioning between partners. The proposed clasper function offered a practical solution to that challenge. The discovery carried another layer of interest because similar behavior occurs in living horseshoe crabs. During spawning, Male horseshoe crabs use modified limbs to attach themselves to females as eggs are deposited. At first glance, the resemblance appears striking. Two marine arthropods, separated by immense spans of evolutionary history, seem to employ comparable strategies during reproduction. The connection, however, does not imply close kinship. Trilobites and horseshoe crabs belong to different branches of the arthropod family tree. Their shared use of clasping structures represents convergent evolution, a process in which unrelated organisms arrive at similar solutions when faced with similar biological problems. Across hundreds of millions of years, separate lineages can sometimes produce echoes of the same idea. Other fragments of evidence had appeared before the clasper discovery. Some fossils preserve tiny spherical structures interpreted as eggs. In one case, unfertilized eggs were found sheltered beneath the head shield of a specimen believed to be female. Elsewhere, clusters of fertilized eggs occur within Cambrian sediments. Certain fossil beds also contain unusually dense accumulations of trilobites gathered together at the same time. Such assemblages may record communal molting events, reproductive gatherings, or combinations of both behaviors. Viewed together, these clues reveal creatures whose lives were more behaviorally sophisticated than their shells alone might suggest. The clasper-bearing Olenoides fossil demonstrated that specialized mating adaptations already existed more than 500 million years ago. In seas populated by some of Earth's earliest complex animal communities, trilobites were already engaging in reproductive behaviors that required anatomical specialization, coordination, and evolutionary refinement. Even at that distant stage of life's history, the rhythms of courtship and reproduction had become woven into the fabric of the living world. A trilobite lifted from stone in Morocco may belong to the same broad lineage as one found in Canada, China, Australia, or Antarctica. Few animal groups left behind a record so geographically expansive. Their remains appear across nearly every corner of the modern world, scattered through cliffs, quarries, deserts, mountain ranges, and polar landscapes. Long after the animals themselves vanished, traces of their existence endured within rocks that would later be carried across continents and through immense geological change. Part of that success comes from the material from which their exoskeletons were built. Calcite provided protection during life, yet it also offered an unusual advantage after death. Shells composed of calcite possess a greater chance of surviving burial, compression, and mineral replacement than many softer biological structures. Through hundreds of millions of years, those mineralized remains persisted while mountain chains rose, oceans opened and closed, and entire regions shifted across the face of the planet. The world trilobites inhabited looked very different from the one visible on a modern globe. During much of the Cambrian, familiar continents did not yet exist in their present arrangement. Landmasses that would eventually become North America, Europe, and parts of Asia occupied separate positions, while the immense southern supercontinent Gondwana united what are now Africa, South America, India, Australia, and Antarctica. Between these lands stretched broad continental shelves flooded by shallow seas, creating habitats that suited trilobites exceptionally well. Across those waters, different species adapted to local conditions. Some occupied warm equatorial environments where sunlight penetrated clear seas. Others lived in cooler regions, approaching higher latitudes. Geographic barriers, changing sea levels, and shifting coastlines encouraged populations to diverge. Through time, one lineage became many, and many became thousands. The result was a distribution so widespread that trilobites effectively became citizens of a planetary marine network. Their abundance produced a legacy extending beyond biology. Because particular trilobite species existed during specific intervals of geological time, they serve as valuable markers for scientists studying ancient rocks. A geologist examining a fossil bearing layer can often identify its age by recognizing the trilobites preserved within it. Fossils that perform this role are known as index fossils. They allow rock layers, separated by enormous distances, to be matched with one another, creating a shared timeline across continents. This usefulness has been especially important for Cambrian geology. The rapid diversification of trilobites generated numerous distinctive forms that appeared and disappeared in relatively predictable sequences. Those patterns provide a framework for correlating strata in regions that may now lie thousands of kilometers apart. A fossil discovered in one country can help establish the age of rocks in another, linking distant places through creatures that disappeared hundreds of millions of years ago. Their influence reaches beyond scientific fieldwork. In Dudley, England, the trilobite Calamine blumenbachii became so closely associated with local identity that it earned a place at the center of the town's coat of arms. Across the Atlantic, students in Ohio successfully petitioned for Isotellus maximus to become the official state fossil in 1985. Such honors reflect an enduring connection between people and these long extinct animals. Trilobites conquered no land and built no monuments, yet their presence remains woven into both Earth's geological record and human culture. Sometimes, an entire field can be transformed by a single discovery, not through the recovery of a larger skeleton or the identification of a new species, but through a fossil that preserves familiar creatures in a level of detail no one expected. More than 500 million years after the animals themselves disappeared, a remarkable deposit in Morocco offered one of those rare moments. In June 2024, an international team led by Professor Abdurazak El Albani of the University of Poitiers published a study in the journal Science describing trilobites from the high Atlas Mountains. The fossils were so extraordinary that they quickly acquired a memorable nickname, the Pompeii trilobites. The comparison captured the nature of their preservation. Like the inhabitants of the Roman city overwhelmed by volcanic catastrophe, these Cambrian animals were caught in a sudden event that recorded details normally lost forever. The story began more than 500 million years ago in a shallow marine environment situated near active volcanism. A pyroclastic flow surged into the region carrying superheated ash and volcanic debris. The event unfolded rapidly enough that organisms living on the seafloor were buried almost immediately. Instead of being scattered by currents, consumed by scavengers, or broken apart during decay, their bodies became entombed within fine volcanic material. Such preservation created something exceptionally rare. Trilobite fossils are usually known from their hard exoskeletons because mineralized parts survive far more readily than soft anatomy. In these Moroccan specimens, however, the ash captured features extending far beyond the shell. Entire body segments could be examined in 3 dimensions. Delicate appendages remained attached. Hair-like structures, known as setae, projected from the limbs. Clusters of specialized legs surrounding the mouth survived with striking clarity. Researchers could also investigate anatomical details that ordinarily vanish before fossilization. Portions of the digestive system remained visible within the body. The hypostome, a plate associated with the mouth region, could be studied in its natural position. The labrum, functioning as an upper lip, was preserved as well. These structures provided an unusually complete view of trilobite biology, allowing scientists to move beyond external appearance and examine how the animals function during life. The fossils revealed another layer of information. Tiny organisms attached to trilobite shells remained fixed exactly where they had been when burial occurred. Their positions were preserved with such fidelity that researchers could reconstruct interactions taking place at the moment catastrophe struck. The deposit captured not only anatomy, but also ecological relationships frozen within a single instant of Cambrian time. Among the most important findings concerned feeding. Dense inward facing spines lined appendages near the mouth, forming structures well suited for directing food toward processing surfaces. Comparisons with living horseshoe crabs proved especially informative. Although separated by vast evolutionary distance, both groups employed appendages that performed broadly similar mechanical functions. Evidence from the Moroccan fossils helped resolve long standing debates regarding how trilobites gathered and handled food. Experienced paleontologists were astonished by the quality of preservation. John Patterson described his immediate reaction as one of disbelief, while Greg Edgecombe remarked that these fossils came closer to resembling living animals than any trilobites he had studied during decades of research. For creatures that vanished hundreds of millions of years ago, the distance between past and present suddenly seemed much smaller. Growth posed a peculiar challenge for trilobites. Their exoskeleton provided protection, structural support, and attachment points for muscles, yet that same armor imposed a strict limitation. A rigid shell cannot expand as the body inside grows. At intervals throughout life, each trilobite faced the same unavoidable task. To become larger, it first had to abandon the protection that had carried it safely through the sea. This process, known as ecdysis, linked trilobites to the broader arthropod lineage. Growth occurred in stages, rather than as a continuous progression. The old exoskeleton separated from the tissues beneath it, and the animal gradually worked its way free. For a brief period afterward, the new outer covering remained soft and flexible. Water entered the body, causing temporary swelling that expanded overall size before the fresh exoskeleton hardened into its final form. That vulnerable interval carried significant risks. An armored trilobite could withstand many hazards of Paleozoic life. A recently molted trilobite possessed few such advantages. Muscles and limbs remained functional, but the protective shell had not yet regained its strength. Predators roaming nearby waters would have encountered animals far less capable of defending themselves than they had been only hours earlier. The fossil record preserves abundant evidence of this recurring event. In fact, many specimens displayed in museums are not the remains of dead trilobites at all. They are discarded exoskeletons, known as exuviae, left behind after successful molts. Because a single individual could shed its shell numerous times throughout life, each trilobite contributed multiple exoskeletons to the sediment. Death produced only one body. Molting produced many fossils. Distinguishing between the two has become an important task for paleontologists. Molts frequently exhibit characteristic patterns of separation. The head region often detached along specialized facial sutures, creating openings through which the animal could emerge. Fossils preserving this arrangement commonly indicate a successful molt. Fully articulated specimens with all body parts connected are more likely to represent actual deaths, though even that distinction can sometimes remain uncertain. Evidence from certain fossil deposits suggests that some species may have synchronized their molting activities. Large accumulations of trilobites appear in specific layers, raising the possibility that groups gathered together during vulnerable stages of life. Modern horseshoe crabs display comparable behavior, assembling in substantial numbers during critical biological events. When many individuals molt simultaneously, predation pressure becomes distributed across a crowd rather than concentrated on isolated animals. The developmental journey of a trilobite unfolded through several recognizable stages. Life began with a tiny larval form called a protaspis. As growth continued, the animal entered successive meraspes stages, during which additional thoracic segments appeared. Each molt brought subtle changes in shape and complexity. Eventually, growth stabilized in the adult holaspis stage, where the full complement of segments had been achieved. Patterns of development varied considerably among species. Some added segments rapidly, while others followed different schedules. The number of molts required to reach adulthood could also differ. These variations created another dimension of trilobite diversity, woven alongside differences in ecology, anatomy, and geography. Molting carried consequences, extending beyond growth itself. Every shed exoskeleton had to be rebuilt using minerals drawn from the surrounding environment. Changes in seawater chemistry therefore influenced more than survival. They affected the very process through which trilobites developed, matured, and maintained the armor that defined their existence. Vision was never a single invention in trilobite history. Across hundreds of millions of years, different lineages arrived at different solutions to the same challenge, gathering information from a world shaped by water, distance, sediment, and light. Their fossilized eyes reveal a story of experimentation, one in which evolution repeatedly adjusted the design of sight to match the demands of particular environments. The most widespread arrangement was the holocrol eye, a structure that appeared early and persisted across much of trilobite history. These eyes contained numerous tiny lenses, sometimes numbering in the thousands, packed tightly together beneath a single transparent membrane. Seen under magnification, they resemble a mosaic assembled from countless mineral windows. Such eyes were especially effective at detecting movement across broad fields of view. In busy marine environments, where danger and opportunity could approach from many directions, this design provided a steady stream of visual information. Within another lineage, a strikingly different approach emerged. Members of the order Phacopoda evolved the schizocrol eye, one of the most distinctive visual systems known from the fossil record. These eyes possessed far fewer lenses, often only several dozen, yet each lens was dramatically larger than those of holocrol eyes. Every lens carried its own individual corneal covering, creating an arrangement unlike that seen in any living animal. When viewed on a fossil, the eye resembles a cluster of polished beads set into the head. Large calcite lenses introduced optical challenges of their own. Calcite bends light differently depending on its orientation, an effect that can blur images passing through thick crystals. Earlier sections traced how certain trilobites addressed this difficulty through complex doublet lens structures that corrected distortions before the light reached sensory tissues. The presence of such refinements reveals that visual performance remained under strong evolutionary pressure. Clearer vision could influence feeding, navigation, mate recognition, and avoidance of predators. A third eye type appears much less frequently in the fossil record. Known as the abathocrol eye, it belonged to members of the Cambrian order Eodicina. These eyes consisted of relatively small lenses, spaced farther apart than those of other trilobites, with each lens possessing its own cornea. Fossils preserving this arrangement are uncommon, leaving many aspects of its function uncertain. Even so, Their existence broadens the range of visual strategies known within the group and hints at developmental pathways that later disappeared. Not every trilobite relied on sight. Several lineages abandoned eyes altogether. Fossils from these species preserve smooth head shields where visual organs once existed. Such changes occurred repeatedly and independently, indicating that blindness evolved more than once. In habitats where light scarcely penetrated, maintaining elaborate eyes offered little advantage. Energy and resources could instead be directed toward other sensory systems better suited to darkness. This pattern illustrates a broader principle woven throughout the history of life. Evolution does not move toward a single ideal form. It responds to local circumstances, modifying structures according to the demands of particular environments. Trilobite eyes varied because the worlds they inhabited varied as well. From dense lens mosaics to giant optical crystals, from rare Cambrian experiments to complete blindness, trilobites explored an extraordinary range of visual possibilities. Their story is not merely about seeing, it is about matching perception to place and adapting the tools of awareness to the conditions of a changing planet. By the middle chapters of trilobite history, evolution had begun experimenting in directions that would have seemed improbable during their early rise. Many species still carried the familiar outline that had served the group for hundreds of millions of years, yet scattered among them were forms so unusual that they appear almost like creatures imagined rather than discovered. Their fossils reveal a period when natural selection explored extremes of shape, display, and sensory design. Among the most striking was Wallocerops trifurcatus, a Devonian trilobite whose head supported an extraordinary three-pronged structure projecting forward like a trident. In some specimens, this projection stretched nearly the length of the entire animal. Additional horns rose above the eyes, while rows of spines decorated the body. The result was a silhouette unlike that of almost any other trilobite known. For years, researchers debated the purpose of the trident. Some proposed that it disturbed sediment while the animal searched for food. Others suggested a sensory role. More recent studies have pointed toward a different possibility. The structure bears intriguing similarities to the exaggerated horns found in many modern beetles, features shaped through competition between males. In this interpretation, Wallocerops may have used its trident in ritualized contests for access to mates, making it a possible example of sexual selection operating roughly 400 million years ago. Its anatomy contained another surprise. Certain spines curved in ways that disrupted the bilateral symmetry normally expected in arthropods. Detailed examination indicates these asymmetries were consistent and genetically controlled. They were part of the animal's design, not the result of injury or developmental error. Such departures from conventional body plans demonstrate how flexible trilobite evolution could become under particular pressures. Another Devonian species, Erbinochle, erbini, approached the world through an entirely different innovation. Its eyes rose high above the head on vertical towers, creating one of the most distinctive visual systems ever produced by an arthropod. More than 400 lenses were arranged in stacked columns, with some files reaching 18 lenses in height. From these elevated platforms, the animal could monitor nearly every horizontal direction, including regions behind its own body. Each tower also carried an overhanging ridge at the top. These structures functioned much like eye shades, reducing glare from overhead sunlight. Their presence offered an important clue about behavior. As paleontologists Richard Forty and Brian Chatterton observed in a 2003 study, eye shades would have little value in darkness. The adaptation strongly suggests that at least some trilobites spent significant time active under daylight conditions. A third example, Dicranurus monstrosus, seemed almost sculpted from curling blades. Long spines projected from the head and swept outward in dramatic arcs, creating an appearance that immediately captures attention. Fossils of this species rank among the most sought after trilobite specimens in the world. Preparing such fossils demands extraordinary patience. Many are preserved within dense limestone, requiring specialists to work beneath microscopes for 40 to 60 hours. Air abrasive tools remove tiny amounts of rock at a time, gradually revealing each delicate spine. Through that effort, forms hidden for hundreds of millions of years emerge once more, preserving some of the strangest experiments ever conducted by trilobite evolution. A trilobite crossing the seafloor may have appeared insignificant when viewed beside giant predators, reef builders, or drifting swarms of plankton. Yet ecosystems are often shaped by organisms whose influence comes not from size, but from persistence. Across much of the Paleozoic, trilobites altered the physical and chemical character of the ocean floor through countless ordinary activities repeated generation after generation. One of their most important contributions came through movement within sediment. Many species burrowed as they searched for food, shelter, or protection. Every passage disturbed layers of mud and sand, turning material that might otherwise have remained undisturbed for long periods. This process, known as bioturbation, transformed the structure of the seabed. Sediment particles were mixed, organic matter was redistributed, and pathways opened through which water could penetrate deeper into the substrate. The significance of this activity becomes clearer when viewed against the backdrop of earlier marine environments. Before widespread burrowing evolved, much of the seafloor was covered by microbial mats, dense communities of microorganisms forming continuous living surfaces. These mats acted almost like biological carpets. Trilobites belonged to the growing collection of animals that disrupted this arrangement. Their feeding and digging broke openings through those layers, allowing circulation patterns within the sediment to become more complex than they had been before. As oxygen-rich water reached deeper zones, chemical conditions changed. Microbial communities shifted. Nutrients moved more freely between sediment and seawater. Small organisms gained access to habitats that previously did not exist. A burrow left by one trilobite could influence a chain of ecological interactions extending far beyond the animal that created it. Across millions of years, repeated disturbances reshaped entire marine landscapes. Feeding behavior contributed another layer of influence. Numerous trilobites grazed upon microbial films and organic material coating the seafloor. This constant consumption prevented particular communities from dominating large areas for extended periods. Resources remained available to a wider range of organisms, encouraging diversity across benthic ecosystems. Through ordinary feeding, trilobites helped maintain dynamic biological communities instead of static ones. Their abundance amplified every effect. During intervals of peak success, trilobite populations likely numbered in the billions. Each individual processed sediment, consumed organic matter, produced waste, and interacted with surrounding organisms. Collectively, these actions moved enormous quantities of material through marine food webs. Nutrients absorbed in one location could be redistributed elsewhere through feeding, digestion, and excretion, linking different parts of the ecosystem into a broader cycle. Growth added yet another contribution. Because trilobites molted repeatedly throughout life, vast numbers of discarded exoskeletons accumulated on the seafloor. These remains contained substantial amounts of calcite. As exuvii broke apart and became incorporated into sediment, they contributed mineral material that would eventually participate in the formation of carbonate rich deposits. Layer upon layer of marine sediment incorporated fragments of trilobite armor into the geological record. Their ecological role also extended upward through food chains. Trilobites served as prey for larger arthropods, cephalopods, fish, and other predators. Energy originating with microbes, detritus, and microscopic producers could pass through trilobite bodies before reaching higher trophic levels. They formed a living bridge between foundational sources of productivity and the animals occupying upper positions within Paleozoic ecosystems. For hundreds of millions of years, trilobites did more than inhabit ancient oceans. Through burrowing, grazing, molting, nutrient cycling, and their place within food webs, they helped construct the environments around them. The Paleozoic seafloor was shaped in part by their continual presence, one small movement at a time. Along the shores of modern oceans, an observer can still encounter an animal whose outline feels strangely familiar. Its body is protected by a broad armored shell. Compound eyes sit upon its surface. Segments are concealed beneath a rigid exterior, and its life unfolds largely along the seafloor. Although separated from trilobites by immense spans of time and evolutionary history, the horseshoe crab carries echoes of forms that once dominated Paleozoic seas. The resemblance is not an illusion. Horseshoe crabs and trilobites shared several broad features shaped by life in similar environments. Both possessed hardened exoskeletons that provided protection while supporting movement across sediment. Both relied on compound eyes assembled from many visual units. Both occupied lifestyles closely tied to the seabed, where feeding, mating, and survival depended on navigating complex marine landscapes. Such similarities have inspired comparisons for generations and helped establish horseshoe crabs as one of the most recognizable living parallels to trilobites. Reproductive behavior provides one of the most intriguing points of connection. Earlier evidence from Cambrian trilobites revealed specialized clasping appendages interpreted as structures used by males during mating. Horseshoe crabs employ a comparable strategy today. During spawning events, males attach themselves to females using modified limbs and remain connected while eggs are released and fertilized. The mechanical details differ, yet the broader solution displays a striking resemblance. Large gatherings offer another parallel. Modern horseshoe crabs often converge in enormous numbers along coastlines during breeding seasons. Beaches can become crowded with overlapping shells as animals emerge from the water to reproduce. Paleontologists have long puzzled over fossil deposits containing dense accumulations of trilobites preserved together. Although several explanations remain possible, some assemblages may represent comparable social concentrations linked to molting, reproduction, or seasonal behavior. Despite these similarities, horseshoe crabs are not descendants of trilobites. Their evolutionary histories diverged deep within the arthropod family tree. Horseshoe crabs belong to the chelicerates, a lineage that also includes spiders, scorpions, mites, and ticks. Trilobites occupied a separate branch much closer to the foundation of arthropod evolution. The resemblance between the two groups reflects convergent evolution, the repeated emergence of similar solutions among unrelated organisms facing comparable ecological challenges. That convergence becomes even more striking when viewed across time. Horseshoe crabs have existed for roughly 450 million years. Their history overlapped with trilobites for most of the Paleozoic era. They witnessed the rise of jawed fish, the assembly of Pangaea, and the environmental upheavals that eventually erased trilobites from the planet. When the end Permian catastrophe arrived, horseshoe crab ancestors endured while trilobites vanished. Exactly why one lineage survived and the other disappeared remains difficult to answer with certainty. Horseshoe crabs may have benefited from broader habitat preferences, including tolerance for brackish environments where fresh and salt water mix. Wider ecological flexibility can provide refuge during periods of environmental instability. Chance also plays a role in survival. Extinction bottlenecks sometimes hinge upon which populations happen to persist long enough for recovery to begin. Today, horseshoe crabs face pressures of their own. Coastal development alters spawning habitats, while harvesting has affected populations in several regions. Their copper-based blue blood remains valuable in pharmaceutical testing because it can detect bacterial contamination with extraordinary sensitivity. Should horseshoe crabs one day disappear, a distinctive connection to the Paleozoic would disappear with them. Their continued presence offers a living reminder that some evolutionary experiments can endure across nearly 500 million years of changing worlds. A shoreline of the early Triassic would have looked unfamiliar to any creature carried forward from the closing days of the Paleozoic. The catastrophe had passed, yet the ocean that emerged afterward was not a restored version of what had existed before. Recovery unfolded across millions of years, and the rebuilding process followed new paths. Life returned, communities reassembled, and ecosystems expanded once more, but trilobites were absent from every stage of that renewal. The seas gradually filled with organisms that either survived the end Permian crisis or evolved from survivors. Ammonites diversified into a remarkable array of forms and spread through marine environments across the globe. Bony fishes expanded into ecological opportunities left vacant by extinction. Crustaceans became increasingly important occupants of the seafloor, exploring feeding strategies and habitats that once supported numerous trilobite species. Higher in the food web, marine reptiles would eventually rise to prominence, adding new dimensions to predation in the Mesozoic oceans. Ecologists describe part of this process through a concept known as incumbent replacement. Once a successful group becomes established within an ecological role, it gains advantages that make displacement difficult. Resources are already being exploited efficiently. Reproductive populations are already present. Evolution continues, refining adaptations generation after generation. As ecosystems stabilize, opportunities for entirely different groups become increasingly limited. For trilobites, the challenge extended far beyond competition. No remnant population remained to begin a recovery. Earlier extinction events had reduced their diversity, yet survivors always endured somewhere. A handful of species could persist, diversify, and rebuild portions of the lineage. The end Permian event broke that pattern completely. Every known trilobite lineage disappeared. No refuges remained in distant basins. No isolated populations lingered along overlooked coastlines. The thread connecting future generations to their Cambrian origins was severed. Even a hypothetical survivor would have entered an altered world. Ocean chemistry differed from conditions that had shaped trilobite evolution for hundreds of millions of years. Food webs were reorganizing. Competitors were exploring ecological roles with growing success. Predators possessed new capabilities, and evolutionary pressures were shifting in directions unfamiliar to Paleozoic communities. Survival would have required adaptation to a landscape transformed at nearly every level. Extinction carries a finality that is sometimes difficult to appreciate. Species can evolve into new forms, lineages can diversify and branch. populations can recover from severe decline. Once every member of a lineage disappears, however, evolution has nothing left to work with. Natural selection cannot rebuild a vanished group from memory. The precise combination of inherited traits that defined trilobites existed only within trilobites themselves. Their story began during the Cambrian, when ecological opportunities were abundant and animal life was exploring possibilities on an unprecedented scale. Across the ages that followed, trilobites survived, shifting continents, changing climates, rising competitors, and multiple extinction crises. They diversified into forms with towers of lenses, sweeping spines, elaborate armor, and lifestyles adapted to nearly every corner of the Paleozoic Sea. When the end finally arrived, it left no descendants behind. The oceans continued, life continued, evolution continued, yet the trilobites belonged entirely to an earlier chapter. Their disappearance was not an interruption awaiting reversal. It marked the permanent closing of one of Earth's longest and most influential evolutionary journeys. A long history can create the illusion of permanence. When a lineage survives for hundreds of millions of years, crossing shifting climates, rearranging continents, and repeated biological crises, endurance can begin to look limitless. Trilobites seem to embody that endurance. They had already persisted through catastrophes that erased countless other organisms. Their fossil record stretches across such immense spans of time that extinction can appear almost incompatible with their story. Yet the deeper pattern tells a different tale. Each major crisis left marks that were not immediately obvious. Survival and recovery are often treated as the same outcome, but they are not identical. A lineage may endure an extinction event while losing species, habitats, geographic range, and evolutionary potential. Those losses can accumulate even when the group itself remains present. The Cambrian brought several disruptions that removed many early trilobite branches. Recovery followed, and during the Ordovician, their diversity expanded dramatically. New forms appeared across broad continental shelves. Ecological roles multiplied. The lineage possessed depth, redundancy, and opportunity. If one branch vanished, others remained. Evolution had many pathways available. The end Ordovician extinction narrowed those possibilities. Numerous species disappeared as climatic upheaval reshaped marine environments. Trilobites survived and diversified again during the Silurian, though the rebound was less expansive than earlier radiations. Diversity returned, yet the overall structure of the lineage had become somewhat leaner. Certain evolutionary experiments had ended permanently. A further reduction arrived during the prolonged crises of the Devonian. Extinction pulses spread across millions of years, steadily removing branches from the trilobite family tree. Entire orders vanished. Distinctive body plans that had taken immense stretches of evolutionary time to develop disappeared from the oceans. Recovery occurred once more, but it was modest. The survivors belonged almost entirely to a single order, the Proetida. A lineage that had once explored countless forms now rested upon one remaining foundation. Viewed mathematically, resilience behaves less like an inexhaustible shield and more like a reserve that can be depleted. Imagine diversity as a network of pathways through time. Every extinction removes routes from that network. Recovery can rebuild some connections, yet rebuilding rarely restores every lost possibility. If losses repeatedly exceed gains, the overall trend continues downward even when survival persists. By the Permian, trilobites remained present across parts of the world, though their diversity had contracted enormously from earlier peaks. Their evolutionary portfolio had become concentrated. Geographic distributions were narrower. Ecological roles were fewer. Adaptations that once spanned a broad range of environments existed within a much smaller collection of species. Under those conditions, another major crisis carried greater consequences than previous ones. The end Permian catastrophe did not require a special vulnerability unique to trilobites. It encountered a lineage already operating with limited reserves. There were fewer species to absorb losses, fewer habitats providing refuge, and fewer evolutionary alternatives waiting in the wings. This perspective reshapes the meaning of their disappearance. Trilobites were not fragile organisms that failed at the first sign of adversity. They endured challenges across nearly 300 million years. Their extinction emerged from a different reality. Strength had carried them through repeated disasters, but every survival extracted a cost. When the final catastrophe arrived, the accumulated debt of earlier crises left no margin remaining, and resilience itself had reached its limit. Long after the last trilobite vanished from the oceans, another species became fascinated by them. Humans encountered their fossilized remains in cliffs, riverbanks, deserts, and quarries, often without knowing what they represented. Across different cultures and different centuries, these stone impressions attracted attention for the same reason they attracted today. Their forms seemed deliberate, intricate, and strangely familiar, as though fragments of another world had been pressed into rock and left waiting to be discovered. Among the indigenous peoples of North America, trilobite fossils were collected centuries before paleontology emerged as a formal science. The Ute people of what is now Utah carried certain trilobite fossils as protective objects. Their segmented shapes became part of local traditions and beliefs, demonstrating that these fossils possessed cultural significance long before scientists attempted to reconstruct their evolutionary history. Similar patterns appeared elsewhere. Aboriginal Australians also collected fossils, recognizing them as noteworthy objects embedded within the landscape. As geological study expanded in Europe, trilobites became some of the most recognizable fossils ever found. Few places illustrate this better than Dudley in England. Limestone quarries around the town yielded large numbers of specimens, particularly the species Calamane blumenbachi. Collecting became so widespread that the fossil acquired a local nickname, the Dudley locust. Its popularity eventually extended beyond private collections and scientific cabinets. The trilobite became a symbol of the town itself, earning a place on Dudley's coat of arms and linking local identity to a creature that had disappeared hundreds of millions of years earlier. The fascination has never faded. Today, trilobite collecting exists on a global scale. Common species can be purchased for the price of a book or a museum ticket, allowing students and enthusiasts to hold a tangible piece of deep time in their hands. At the opposite end of the spectrum, exceptional specimens command substantial sums. Complete examples displaying rare anatomical features, unusual preservation, or spectacular ornamentation can sell for thousands of dollars. Much of the modern market centers on Morocco, particularly the fossil-rich rocks of the Atlas Mountains. Devonian trilobites from these deposits are celebrated for their extraordinary appearance. Species such as Wallazorops, Erbanocchile, and Dicranurus have become icons among collectors because of their tridents, towering eyes, and elaborate spines. Extracting such fossils from limestone is an art as much as a technical process. A single premium specimen may require 40 to 60 hours of preparation beneath a microscope. Using air abrasive tools, preparators remove rock grain by grain, revealing structures delicate enough to break under a careless touch. This trade, occupies a complicated space between commerce and science. Commercial fossil hunters have uncovered remarkable specimens that later became the subjects of important research. Museums and researchers frequently benefit from discoveries made by skilled collectors working in remote regions. At the same time, financial incentives can encourage forgery. Added spines, composite fossils assembled from multiple individuals, and entirely fabricated specimens have all appeared within the marketplace. Valuable fossil localities can also suffer damage when excavation prioritizes quantity over preservation. Even so, the story remains unfinished. More than 25,000 trilobite species have been formally described, and new species continue to enter the scientific record. Every newly discovered specimen adds another detail to a narrative that began in Cambrian seas. The animals themselves are gone, yet their remains continue to pass from stone into human hands, carrying fresh information across 500,000,000 years. Try approaching the number from a different direction. Imagine a single lineage beginning its journey near the dawn of complex animal ecosystems, then continuing through age after age, while mountains rise, continents separate, climates shift, and entire communities of organisms appear and disappear. That span is the scale of trilobite history. It stretches so far beyond ordinary experience that comparison becomes one of the few tools capable of bringing it into focus. The age of mammals feels immense from a human perspective. Since the extinction of the non-avian dinosaurs, mammals have diversified into whales, bats, elephants, primates, and countless other forms. Yet, that entire interval, from 66 million years ago to the present day, could fit within trilobite history nearly 5 times. The period that contains every mammal, every bird alive today, and every human who has ever lived occupies only a fraction of the time trilobites spent in Earth's oceans. The dinosaurs offer another measure. Their story began during the Triassic and ended with the asteroid impact at the close of the Cretaceous. They ruled terrestrial ecosystems for roughly 165 million years, a duration so vast that it often seems unmatched. Trilobites endured for considerably longer. Their lineage had already survived countless generations before the first dinosaur appeared, and their history exceeded the entire age of the dinosaurs by more than 100 million years. Humanity occupies a far smaller sliver of time. Anatomically modern humans have existed for approximately 300,000 years. Written history covers only a tiny portion of that interval. Agriculture emerged within the most recent moments of the human journey. If trilobite history were compressed into a single day, the appearance of modern humans would occur within a fraction of the final second before midnight. Entire civilizations would pass too quickly to register. Across those hundreds of millions of years, Earth never remained still. Continents drifted across the globe and repeatedly assembled into new configurations. Oceans expanded and contracted. Ice sheets advanced and retreated. Atmospheric chemistry shifted. Coral reefs flourished, collapsed, and flourished again. Forests spread across land for the first time. Vertebrates emerged from the water and began exploring terrestrial environments. Throughout these transformations, trilobites persisted as participants in a continually changing world. Their success was not static. New species evolved, old forms disappeared, ecological roles shifted, diversity surged during some intervals and contracted during others. Survival demanded adaptation again and again. Each geological period presented new circumstances, and trilobites repeatedly found ways to endure them. Their longevity was built from countless acts of evolutionary adjustment occurring across unthinkable stretches of time. That perspective makes their absence all the more striking. A lineage capable of surviving for nearly 270 million years ultimately reached an endpoint. The fossil record preserves the evidence of their achievements, their recoveries, and their setbacks, yet no living representative remains. Seen from this distance, extinction becomes something larger than defeat. Trilobites were among the most successful animal groups Earth has ever produced. Their disappearance illustrates a broader truth woven through natural history. Longevity does not create permanence. Adaptation does not guarantee eternity. Even the most enduring lineages occupy a finite chapter within the larger story of life, and the trilobites carried theirs farther than almost any that came before or after. Far below modern landscapes, beneath cities, forests, deserts, and mountain ranges, layers of stone preserve fragments of worlds that no longer exist. Within those layers rest trilobites, entombed in limestone and shale, deposited on seafloors hundreds of millions of years ago. Their bodies vanished long ago, transformed by geological time into mineral traces. Yet one feature remains especially striking. The eyes that once surveyed Paleozoic oceans still endure within the rock. Most eyes are temporary structures. They depend on living tissue, delicate cells, and biological chemistry. When life ends, those components quickly break apart. Trilobites followed a different path. Their lenses were constructed from calcite, a transparent mineral already familiar to the surrounding seafloor. From the moment those lenses formed, vision and geology became intertwined. The organs responsible for gathering light were also crystals, built from the same substance that would later preserve them. That unusual design produced a legacy unmatched in the history of animal life. The lenses did not rot away after death. They remained embedded within the exoskeleton, protected as sediments accumulated overhead. Pressure increased. Oceans retreated. Continents wandered across the globe. Through all those changes, the mineral architecture of countless trilobite eyes survived. Even today, paleontologists can examine individual lenses and study details of optical systems that first evolved more than 500 million years ago. A fossil trilobite may appear motionless and remote, yet its eyes still reveal traces of their original function. Light entering a well-preserved calcite lens follows pathways determined by geometry established during the Cambrian. The physical principles remain unchanged. Refraction operates today exactly as it did when the animal was alive. In certain specimens, researchers have demonstrated that the lenses can still focus light, preserving the optical properties that once helped an arthropod navigate an unfamiliar world. There is something remarkable in that continuity. Oceans changed beyond recognition. Entire ecosystems disappeared. Mountain chains rose from sediments that once rested beneath waves. Species came and went, in numbers beyond calculation. Through every transformation, these crystal structures persisted as tiny records of a vanished experiment in vision. They are reminders that evolution does not follow a single design. At one moment in Earth's history, an animal lineage solved the challenge of seeing by turning stone into an optical instrument. The trilobites themselves can no longer respond to light. Their final representatives disappeared during the catastrophe that closed the Paleozoic era. No living descendant carries their exact body plan forward. Yet the eyes remain, preserved in museum drawers, research collections, private cabinets, and outcrops scattered across every continent. Each fossil contains a connection between biological innovation and geological endurance. When viewed across the sweep of their history, those eyes become fitting symbols of the trilobite story itself. They first opened in oceans inhabited by some of the earliest complex animal communities. They witnessed diversification, competition, migration, extinction, and recovery across nearly 270 million years. Their owners vanished, their ecosystems dissolved, and their world gave way to another. The lenses endured. In stone chambers deep within the earth, and in fossils lifted into daylight by human hands, crystal eyes still face upward. They no longer perceive the world around them, yet they remain precisely shaped for the task they once performed. After 500 million years, they stand as enduring witnesses to a chapter of life that has ended, while the instruments of vision themselves continue to hold their form.